can see.
Good. Everything works. Good morning. I think in the last 2 days, you heard a lot about models and now also about aerosol cloud interactions. And of course, the models are fantastic tools, but the models without the emissions can produce nothing. So a model without emissions is like a car without gasoline. What should it produce? It cannot produce anything. So you have to make sure that you feed the model with the right input from the soil, from the ground, from other sources in the atmosphere, that it can really produce the chemistry and the aerosol physics you want to simulate. Especially when we talk about chemistry and aerosols. So there's a lot of literature about soil, and this could be a lecture for the whole course. I mean, to talk about emissions is really, so this is a very short, rough overview to give you some details. These are both of the two big PIs. Alexander, you still hear me?
Yes.
Because here says internet connection is unstable, but so, okay, if you hear me, then it's good. So we had these two big, very important persons, both were in America. Guy Brosseau was also MPI director in Germany. And they published a new book in 2017, which calls atmospheric, what is it called? Atmospheric chemistry modeling. It's a very nice book, and it has also a very detailed chapter about emissions inside, what you have to take care when you model and what you have to take care on the emissions. So, and I will go, this is a picture for a table from this book, but I will go through some of them and not all. What came into my mind when I saw this figure, and I thought, hey, Daniel and E, what is this? You have there isoprene and methane, but what's about all the other? What's about all the other VOCs like monoterpenes and sesquiterpenes, which play a very important role in the, as you heard in the last days, I think in the aerosol formation also. So on our budget to get the particles in the atmosphere correct. I'm not sure. I have not asked them, but I guess because both of them are more coming from the chemistry side. So they're both atmospheric chemists. They were not so interested in aerosols, and for this reason, maybe they neglected how much emissions we have of all the other VOCs, beside methane and isoprene. But I will talk about them. So let's start with the terrestrial biogenic emissions. So biological organisms emit a wide range of volatile organic compounds, and not only isoprene. So by growth, metabolism, and decay. Photosynthesis and respiration are dominant processes. Photosynthesis converts CO2 to molecular oxygen and release volatile organic byproducts, and that's our VOCs. So methane, we have about, not similar. So there's even higher anthropogenic sources if we trust this table, and this is a little bit older table from Daniel Chekhov. This is not the newest one in these calculations here, but you see also the huge uncertainties. We have higher anthropogenic sources, natural gas, livestock, rice paddies, as we have biological sources. And for those for those who have followed a little bit the COP26 just discussion, what we had in Glasgow, there's now also some strong aim from some countries to reduce, especially work on here to get this methane, because methane is the second important greenhouse gas in the atmosphere. And so this is something where a couple of countries now try to work really intensive. And especially we lose a lot also by natural gas, by transport, and when we get it out of the ground. The difference from methane to, and this is now a little bit away, from methane to CO2 is that methane, the main sink term is with OH. And you see it here, this is the total sinks, 515 teragram methane per year, and 80% is destroyed by OH. So it reacts, whereas CO2 don't react at all in the atmosphere. So methane, we have a chance to attack. So if when we talk about geoengineering, if you would find some way to increase OH, we could also decrease methane in the troposphere. So the lifetime is about 8 to 10 years. The main natural source of methane is wetlands, where bacteria reduce organic carbon to methane under anaerobic conditions. This is, for example, the wetlands, what we see. Some of the methane is oxidized and it rises to the surface and encounters aerobic waters, while the rest escapes to the atmosphere. And we see here very nice all this huge emissions of methane in the boreal region. So where we have a lot of wetlands, we have high emissions also. But we also have it in the rainforest. We have high sources of emission rates of methane. The estimate here for the biogenic is 270 teragram. And there you see how it differs also. It's not always that everybody gets the same value of emissions. So it's not easy also to really get good estimates for quantification of the methane emissions from all these huge sources. And what we see also for methane quite interesting is that we see a quite nice northern southern hemisphere gradient, and we see also a nice summer winter behavior. And we see that the main sources, they are all in the northern hemisphere. That's the reason the methane concentration is, what is it here? It's about 200 ppb higher in the northern hemisphere compared to the southern hemisphere. Terrestrial biogenic emission non-methane volatile organic compounds, BVOC. And they, of course, are for great interest if you do aerosol research in the atmosphere. So terrestrial plants are the largest global source of non-methane VOCs. Major species emitted are isoprene, terpenes, sesquiterpenes, alkanes, carbonyls, and alcohols. They may be emitted as byproducts of photosynthesis, as responses to injury, and from metabolism and decay. Emission fluxes depend on plant type, life stage, and foliage density, on radiative and meteorological variables within the canopy, and on external perturbations such as cutting, air pollution, and insect infestations. So if you look normally at a plant, a tree, what is the goal? The goal of the tree is to get enough CO2, which it gets from the air. It's to get enough water from the ground, over needles and the leaves. It tries to get enough sunlight because it needs it for the photosynthesis. It needs uptake of nutrients from the soil, and it tries to prevent damage caused by insects, herbivorous, drought, and hazardous chemicals, stress factors. So if there's enough water, enough nutrients, enough CO2, enough sunlight, then the tree is happy and will also produce these VOCs. So these volatile organic compounds, which then react with OH, ozone, NO3, and can form particles, aerosols, and also, as we just heard in the lecture before, has a huge impact on the cloud interactions, the cloud formation. If we go a little bit more into detail, what are these VOCs? Isoprene is the most important one. It's about 40% of all emitted VOCs are isoprene. It's a C5H, so it has 5 carbon atoms and H hydrogen carbon atoms. And if you multiply them by 2, you come to a monoterpene, a C10H16. So in the plant, the tree forms isoprene, and then it can also, based on this, it can put together 2 isoprenes and form a monoterpene. And if it adds another isoprene, you see a C15H24. It's nothing as taking this times 3, you get sesquiterpenes. And especially this guy, these monoterpenes and sesquiterpenes are very important in aerosol research, atmospheric aerosol research. But you have others, you have aldehydes, you have ketones, depending on the functional groups. You have a lot of other compounds which are also emitted. But our special focus is on these terpenes when we talk about aerosol research. So is there one monoterpene? We talk always about alpha-binding, but no, there are many of them. So, and the good thing is in Hytila, for example, at our research station in Hytila, SMER station, I think you have lectures on this also in the next days. You will hear more about the station. we have measured all this, and there's only 9 now. The good thing is in Hütila, if you take especially this 6 into account, you cover about 90%, more than 90% of the mass of the monoterpenes. So you don't have to put into your model hundreds of them. You can say, okay, I'm happy with 90% of the mass when I take these ones. All have the same molar mass. They're all 136. There's always this C10H16. But they have different reaction rates with OH, ozone, and NO3. And this depends also on the double bind, where it is. It's inside or is it outside, or limonene, as you can see, has 2, so it's more reactive. It has here a double binding and here. So that's the difference. So as said, isoprene is about 40% of all emitted biogenic volatile organic compounds globally. It's about 40%. Then we have methanol, which is 50%, and then already comes alpha-binding. Alpha-binding is in this group, which is 1 to 7% each of them. So alpha-binding is quite important. And then in the next group, which is 0.2 to 1, so about 1%, and there we have already the beta-carophylline. Beta-binding, the trichlorine, these are the other important. And then there comes a group which is less important, which is below 0.2%. And there's also coming some other monoterpenes, for example, camphene and oxymene. So there's a lot of stuff coming out. This figure is from Alex Günther. Alex Günther is one of the PIs in this research, measuring and also modeling the VOCs from the biosphere. And we'll come back to Alex Günther in a second. So, emission inventories. So where we get these numbers from? I mean, we know they're coming from the forest, but it don't help us. We need to have numbers in the models. We need to know to quantify this. How much is really coming out from the tree? And this is the SMER station, and I will not talk about this because I think you have extra lectures. But we have in the SMER station also emission inventories. So there's 2 different kinds of measuring the emissions of the VOCs from the forest. There's one time is direct measurement at the emission source, so you really measure at the source, and the other is an indirect measurement relaxed at the accumulation RIA system. So if you measure at the source, you really enclosure of a certain part from the tree in a cuvette or a Teflon bag. So you can see here in this picture, you have a part of the tree is in this cuvette here. And this cuvette is normally open for a couple of minutes and then it's closing. So there's no exchange with air, with the atmosphere couple, and then it's measuring how much is coming out. And then of course, the forest people who are doing this here at our university, they have to calculate exactly the mass, and then they can give us more or less the number how much monoterpenes or alpha-binding is coming out of so much gram dry leaf of the pine forest, of the pine tree. And this is what we put then in our model. The other way to do is to do it on top of the forest. If you have a homogeneous forest, you can put, and in Hütla, I think it's at 32 meters or 24 meters, you have an relaxed eddy accumulation system. So you measure the wind speed in all 3 directions, and you measure with an instrument which has a very high frequency, the concentration of the gas, and then you can calculate the fluxes. How much is coming from the forest? And this gives you a chance to calculate, to give a good estimate, get a good estimate about how much VOC is coming from the forest out. So here you have it really on a base that you can calculate it per gram, dry needle gram mass, and here you calculate it on the forest area. There's a third way of measuring, and this is from satellites. And satellites have the advantage, of course, they have a global coverage, whereas in Hütila is only one place on the world with a wide, so global coverage with a quite high temperature and spatial resolution is input or evaluation for the global models. No manpower needed for the measurements. In Hütila, we have a lot of people working on this to get this data for us models also. Problems, clouds disable the use of measurements, vertical distribution, very difficult at the moment, but maybe better in the future with the next generation of satellites. So here's a picture from 2005, and I'm really not a satellite person and not up to date how good they are now, but this is formaldehyde in 2005, and they could, of course, you have always the whole column. This is not, there's no vertical resolution, it's just the whole column, how much formaldehyde you have here on this, at this point. I think the satellite's getting better. However, if they could really provide us modelers with vertical distribution of turbines, I'm not sure when this comes. It may come sometime, but I'm not sure when it comes. But it would be great. But we need this emissions from this concentrations from the forests. The other ways. So we just learned that we have this database where you can read it in. So we have database like MEP or Gaia, where they collect all these measurements and data from the model, and you as a modeler can download it and get the data. And they're doing a great job. So it's really the easiest way if you run a regional or global model, can use this data, which are available, which were put together by many scientists, and you can use this data. The other option would be that you have a dynamic description of the emissions in your model. And one code which was actually developed by Alex Günther is the MEGAN code, the model for emission of gases from aerosol in nature, which is, up to my knowledge, the most applied emission code in all Earth system models worldwide. The basic of this code came from 1995 paper from Günther et al. So this is quite easy equation. You have the flux from the emission from the vegetation is nothing else as the foliar density. So this you get from the people from the forest guy who really measure how much trees are there and how much needles you have there. So in kilogram trimeter per square meter. So this you need. Nowadays you get this data also from satellite, or you get it from, they also use some, what is it called, this unmanned UVAs flying around and provide this data. So you need the foliar density. You need to know how much is there, how much amount of needles and leaves per surface area is there. Then you need this epsilon, this ecosystem dependent emission factor at certain temperature and at per 1000 micromole per square meter per second. This is what you get from the forest people who do the cuvette measurements, who really try to estimate how much is coming out from this tree, how much alpha-pinene, how much isoprene is coming out from this tree, from these needles. And this is known as also microgram carbon per square meter per hour. So this you get from the forest people, and this you get from the people who make the cuvette measurements on the trees. And then you need the MEGAN code. And the MEGAN code provides you only this number, this gamma. And the gamma is just an adjustment factor for the dependence on temperature and light emission activities. The interesting thing is we are running this MEGAN code, and the MEGAN code is also a couple of thousand of lines. And it calculates a couple of thousand of lines coding just to produce one number between 0 and 1. Because this tells you how active the tree is, how much active it is at the moment with this temperature. You need to calculate the temperature at the top of the needle, at the bottom of the needle. So that's the reason why it is so computationally expensive to do this. And nowadays, and this is new, this is already, if I say new, it's about 10 years ago. It was not in the early MEGAN version. It's emission activity factor for long-term controls. So it takes into account how was the soil moisture, how is the leaf age, temperature and par averaged over the day and the last 10 days. So Alex Günther and his group found out that it has an impact how warm it was in the last 10 days on the emission now. So when he put this factor into the MEGAN code, which is now available. The MEGAN code is actually free available. So you can actually download, add it to your models and get the emissions. Of course, it's free, but it takes some knowledge about to do it. Good, and with this, Alex Günther published here in a paper, and he published a lot of papers, but this is one of the papers in 2012, where he calculated the distribution of isoprene emissions in January and July. And you can not quite see that you have a lot of isoprene emissions in January here in the Amazon and also in the rainforest in Africa, Australia. And then when we come to July, so in the winter time, there is nothing here from the boreal forest, nearly nothing, no emissions. But then in July, we get also emissions of isoprene here in the boreal forest, and less emissions in the southern part. This data are available. This data are calculated, put on emission inventories like Gaia or Eckart, what we use, and you can download this data. But if you want to have it more detailed, okay, you can also use this Megan code. Put it into a model and say, I want to calculate it by myself because I want to have higher resolution, temporal higher resolution. I want to have a horizontal better resolution because I have the trees from each 500 meters. So then it's better. You can do it with your own model. The isoprene and terpenes react with OH, ozone, and NO3. And you can here see some of them. For the monoterpenes, alpha-badine, for example, has a lifetime of about 2 hours. Isoprene about 2.5 hours, and limonene only less as 1 hour because it has 2 double bond. It can react on 2 different, ozone can attack on 2 different parts on the molecule, and it's the reason the lifetime is much shorter. Beta-caryophyllene is a C15, H24. It's very reactive also. So what we see based on these lifetimes that isoprene and monoterpenes are transported in the boundary layer. So on a nice sunny day, you can say that you see about 50% of the monoterpenes on top of the boundary layer as you see on the ground, because the lifetime is so long that it's well mixed and that you see also high concentrations in the boundary layer, which is normally in Hütila in our research station between 1 and 1.5 kilometers. And we did measurements with balloons up there. And we saw also quite high concentration of terpenes. The sesquiterpenes like beta-caryophyllene, they have such a short lifetime. You will see them not in the boundary layer. You see them on top of the forest, but then they decrease already concentration dramatically because they are just too reactive against ozone. And of course, they all have different reaction rates with different kind of molecules. But this is a nice picture, actually. Boris put this up, where you can say that the isoprene is reacting mostly with OH. So most of the isoprene lost in the atmosphere is by OH, whereas the terpenes react with OH, ozone, and also with a little bit with NO3. So it's more equalized, and sesquiterpenes are reacting mainly with ozone. So that's the weight got lost. Good. Then let's come back to our table and let's now look at NOx. And let's look at NOx, which comes out from the terrestrial biogenic. So we have, if you look at the different sources for NOx, we have the terrestrial biogenic, we have open fires, anthropogenic emission of old quiet, and we have lightning. Nitrogen is essential to live and has an active biochemical cycle in terrestrial ecosystems. Specialized bacteria present in all ecosystems convert atmospheric nitrogen to ammonia, a process called biofixation, and the resulting fixed nitrogen cycles through the ecosystem. Fixed nitrogen can also be directly developed to ecosystem by fertilization. I mean that what we are doing in a quite strong, as we know in our agriculture, or by deposition of atmospheric ammonia and nitrate. Biological processes cycle nitrogen within the ecosystem. So you have assimilation, and you don't have to remember all these words, assimilation, conversion of inorganic nitrogen to biological material. Mineralization, conversion of organic nitrogen to inorganic forms. Nitrification, aerobic microbial oxidation of ammonia to nitrate and onto nitrite and onto nitrate. Denitrification, anaerobic microbial reduction of nitrate to N2. Volatile N2O, which is very important because it's N2O is an important greenhouse gas with a very long lifetime in the atmosphere, so it goes up to the stratosphere. and that has also some impact on the ozone depletion, and NO are generated as byproducts of nitrification and denitrification. There's one thing not mentioned here, but also amines, which have a crucial role. I don't know if you have already lectures of particle formation, cluster formation, and then we know that there's ammonia, and amines have a high potential to form together with sulfuric acid clusters. And amines are also a byproduct from this process what's going on in the soil. There's a nice figure to illustrate this a little bit, but the main message is nitrogen, atmospheric inorganic nitrogen, is taken up by bacteria and other in the soil, bacteria in the soil, and forming this to a kind of nitrogen which can be used by plants. And then we have the emission also from this certain compounds into the atmosphere. Here you see the nitrogen sources from annual emission of NO from soils. And you see especially here where we have a lot of fertilization, a lot of agriculture in the mid latitudes in America, also in Europe. You know, all our tomatoes coming from Spain and Portugal. And Holland is, of course, very important. Here you see a lot of nitrogen. But then we have also NO emissions from the grassland in South America and Africa. This is coming from the drying by the pulsing at the end of the dry seasons. So here in South America and Africa. And now is a good question, where's coming this from India? But I guess it has also something to do with agriculture, mainly to do with agriculture, fertilization. Good, then let's go to open fires. And here we will have a look at the carbon monoxide. So open fire emissions include contributions from wildfires, prescribed fires, land clearing, agriculture management. These emissions are often labeled in the literature as biomass burning, but that leaves it open as to whether biofuels are included. Most fires are set by humans. Also, some wildfires are triggered by lightning. Even when set by humans, fires are not generally classified as anthropogenic in emission inventories because they may have happened anyway, even without human intervention. Fires emit mostly CO2, CO, and H2, but also many other trace species. Emissions depend on the type of vegetation, the vegetation density, and the fire intensity. And here you have, for example, of course, the highest emission is CO2. Here you have different kind of environmentals, savanna and grasslands, tropical forest, extratropical forest, crop, residue, and pasture maintenance. And you see, you have to know what kind of forest you have there or grassland you have there, and then you can see if it burns, what comes out. Then, of course, the most important one is CO. But you see, you get also other stuff coming out depending on the kind what you have. But these data are also available. If you know what kind of forest you have, you can use this table and you can calculate how much emission you will get. Emission of CO from open fires, you can see here, this is now a picture, calculate for 2000, for the year 2000, how much CO is coming out. And we have this, especially in Siberia, we have also a lot of fires. We have a lot of fires going on in Africa and South America, but also in North America up there. But then you have to know also how big is your fire. Is it grassland? Because then you have to get your emission only into the lower part. However, if you have a big fire, a boreal forest fire, then this emission can be much higher. It can be in a couple of kilometers where you really get your input into the atmosphere. Also, there are methods available to calculate this, which height level you should use for emission if you know what kind of forest you have there. But there's a lot of details what you have to worry about if you want to get it correct into your model. Volcanoes play a fundamental role in the cycling of elements on geological timescales by transferring material from the lithosphere to the atmosphere. On the shorter perspective, atmospheric sources and sinks volcanoes are of most interest as sources of ash and sulfur gases, mainly SO2. This is important for us. Yes. Volcanoes often release material in the free troposphere. Large volcanic eruption injects material into the lower stratosphere, what we saw in the last 100 years a couple of times. And the resulting long-lived sulfate aerosol has important implications for climate and for stratospheric ozone. And now we can divide volcanoes. Emissions can be non-eruptive or eruptive. Non-eruptive emissions are released at the volcano mouth, while eruptive emissions are injected in the high altitude. Worldwide database of volcano eruption are available with eruption dates and strengths measured by the logarithmic volcano explosivity index. So for the past, you have all this information, and it's very important for the global models to get this into. For the future, to make prediction, when comes a volcano emission and how important this is of course a little bit a tricky topic for future predictions. This is a nice figure, and we will not go in detail to this figure, but you have it on the script. You can go through it if you read. You see also the radiative impact of this. What was it, 1982? This L12 emissions was also having a big impact on the radiative forcing, and of course the Pinatubo has had also. So this tells you where the volcano is, how strong the emission was, the eruption was, and how much SO2 was emitted. So when you see this, Pinatubo had strong emissions of SO2. Now let's go to the anthropogenic. And now we come to all this. We have the NOx, the CO2, methane, SO2, ammonia, and black carbon. So, and anthropogenic emissions, they're coming from everywhere, as we are aware of. So anthropogenic emissions span a wide range of processes. Most important, combustion, industry, agriculture. And now it gets a little bit tricky. The anthropogenic label in the literature can be ambitious and inconsistent. And this is why you have not just can use the data from the emission industry, you have to read it. You have to understand what is included there. For example, anthropogenic emission inventories include prescribed in agriculture fires, while others do not. Some have it not. Anthropogenic emission inventories typically include emissions of ammonia from agricultural fertilizer, but may not include emissions of NOx from the same process. Regional inventories may include emissions from aircraft in airports, but not in the air. So in the air, then it's not anthropogenic emissions. When it's in the airport, it is anthropogenic emissions. The same is for the ship. Maybe it is included in the port, but not when it is on the sea. Because of definitional problems such as this, care is needed when using anthropogenic emission inventories. It's important to ascertain which sources are included. So this is the very difficult part. You have to understand what is in these emission inventories. Anthropogenic emissions are usually better quantified than other emissions because activity rates are available as economic data, and emission factors are documented for air quality management purposes. Yes, I agree with this sentence completely, but I would add there it depends also a little bit on the governmental situation in the country. Not all governments, as we know, are completely free open with their data, with their emission inventories, as they could be. Emission inventories commonly distinguish between area sources and point sources. Area sources and point sources. So area sources include vehicles, for example, traffic, and other individual small sources for which emissions are distributed over the activity area with best estimates of emission factors. While a point source are concentrated discharges from localized sources, such as a power plant chimney, for example. What comes out from the power plant? Anthropogenic emission inventories are produced by various groups and agencies to serve air quality management and climate modeling needs. And yes, they're doing a great job, fantastic job. But what I realized also that not everywhere we get all the best data. And some governments even sell it. And so it's not completely free open that we have access to all the best data for us, for our models. This is now a nice example for NOx emissions, anthropogenic NOx emission. And you see here also, you can nicely see the ship traffic, how the ship goes, how the airplanes fly here. So this includes both now. So this is anthropogenic NOx emission from the MAG city inventory for the year 2008. Anthropogenic emissions, the same as the biogenic VOCs, we have also anthropogenic VOCs, and here we see that alkanes play a major role, and we have a lot of other, we have alkenes, we have carbonyls, alcohols, and we have aromatics. And aromatics are one compound, sort of compounds which are very important for us when we talk about aerosols, because they have also quite high aerosol yields and can form, especially, and we talk about this high air pollution, what we see just now in India, we saw in the news now that they have big problems, is also related a lot to these aromatics, which are coming from the traffic, for example, from the cars, what we see here. And they're oxidized in the atmosphere, and then they contribute to secondary organic aerosols. They have a short lifetime, as you can see, because they are reacting quite intensively, quite fast. How we get all this VOCs data, we can use the database. So for example, EDGAR, a set of global emission inventories of greenhouse gases or ozone depletion substance for all anthropogenic and most natural sources on a per country basis and on a 1 degree by 1 degree. Another source is EMAP, so European Monitoring and Evaluation Program. So there's a different kind of sources. In my group, we are using the emission of atmospheric compounds and compilation of auxiliary data, ECAT, which has as a combination of different databases. So if you use ECAT, you can, and it's also free available. Of course, you have to register there, but then you can use this free. You can get quite good data. Good. And now let's come to dust and sea salt. So the wind stress on the Earth's surface causes mechanical emissions of aerosol particles, including sea salt, mineral dust, pollen, and plant debris. Sea salt and dust are dominant components of the coarse mode supermicron aerosol over ocean and land, respectively, and generally make important contributions to total aerosol mass concentration and optical death. So pollen and plant debris have more localized influences. Emission of sea salt particles is mostly driven by the entrainment of air into seawater by wave breaking. So resulting air bubbles rise and burst at the sea surface, injecting particles into the air. The emission flux is a strong function of wind speed. So in the great project, what I was coordinating, which was in the years 2012 to 2017, 18, and that's an overview paper which we wrote then in 2019. We did also, so GREAK was a project concentrated on the cryosphere, atmosphere interaction, and climate change. We did also investigation on the sea salt particle emission. So we constructed, in part of this project was also to constructing in Stockholm and partly then later on in Aarhus, these tanks. So the water tanks, where is it? The tanks, in these tanks, air is entrained in real or artificial seawater via fritz, diffusers, or plunging jets. The entrained air breaks up into bubbles which rise to the surface where aerosols are generated by bubble bursting process. So we had artificial, or really, sometimes we used really water from the oceans and put bubbles inside, and then we calculated the amount of particles which we could measure on top here of the water. So the air was got out here to an instrument, to an EMBS system, and then we calculated. Of course, we changed the temperature, different other parameters. And then in the end, we came up with a new parameterization to calculate the sea salt, amount of sea salt particles coming out of the ocean. And of course, it's very related to wind. This is not the new parameterization, but this was an older parameterization, but it just shows here. So you get a lot of these sea salt particles especially where you have high winds in the high latitudes of the southern hemisphere, but also here in the Atlantic, in the northern Atlantic and northern Pacific. You have this high amount of sea salt particles. And now our last point is the dust. So mineral dust is emitted by sandblasting of soils, a process called siltation. Wind lifts large sand particles that travel over only short horizontal distance before falling back to the surface by gravity. And we talk now about particles which are bigger as 15 micrometer. And as you heard in the last days, it's not an aerosol anymore. That's a really big, giant particle already. As the sand particles fall down, they eject dust particles of diameter to be small enough to be transported over the long distance in the atmosphere. These fine particles are classified as clay when they are smaller as 2 micrometer, and as silt when they are between 2 and 50 micrometers. And here we can see that we have a lot of emission of this particle, especially in this area, which is logical, where we have the highest amount of deserts. So here's the Sahara, and here you have a lot of emission. And as we saw also in Finland in the last winter, I mean, I'm coming from Germany, and we had this in Germany, that this Sahara dust particles are transported to Germany. We had it about at least once a year. But we had also some Sahara dust in Finland was it last year or this year in spring? And this was quite unusual that it traveled, the Sahara dust traveled so far from Africa down. So we have to take this also into account into our models. So we cannot do this in 45 minutes to talk about all the different. I want just pick the couple of sources where I thought it's important or it's interesting. But in general, if you want to run your model, you have to take everything into account. You need the biogenic emissions, you need fires, you need the anthropogenic emissions, you need what comes out of the soil. We didn't talk about VOCs. We nowadays know also that there's coming also different kind of VOCs out of the water. Of course, there's living material in the water, there's plankton and everything that is also producing VOCs. So we know that there's also coming seas. We only talked about the sea salt particles. All this you have to take into account. And if you are able to consider all this and also taking the airplanes which flying around, then you can start your model run. And then you can be hope that your model is producing the right atmospheric concentration of gases and then aerosols. But without, if you miss one of the big sources, then your whole budget in your model will not work. Good. I think that's all for me.